The next thing I want to think about is what actually happens during the collision. So when two objects collide, do they just instantaneously bounce off each other? And the answer is no. That would actually break the rules of physics if that were the case. Everything, when it bounces off at something else, it's going to behave a little bit like a spring. It's going to be a little bit elastic, and they're going to bounce. Even pool balls that are very hard, they touch for like a very, very small amount of time, but in that time, they're actually squishing together and spreading back out again to bounce off each other. So we can sort of exemplify this on a bigger scale or on a slower scale if you were to put a spring between two objects. And let's assume this is like a perfect spring that doesn't waste any energy. So we have the same pool balls in this question, example 2, where this is the one, I made this one the 251 because it was going to the right. And then at, 3 meters per second? And then we had the other ball moving to the, this one's moving to the left, the other one's moving to the right. 4 meters per second, 200 grams, right? Now the difference here is we're gonna put a spring between these. So let's pretend there's a spring that's like attached to one of the balls, for example, and this spring is gonna act like a perfect spring. So they're gonna bounce off each other with this spring. So what all that does is it basically slows down the interaction between these two balls. So it's not so instantaneous, right? The same thing is gonna happen as if they were to hit without the spring. It just happens at a slower rate so we can visualize it a little bit better. So the question is, how much would the spring be compressed when the 200-gram ball stops moving? Because when these two balls are colliding towards each other, as they hit the spring, as the spring hits, they're going to slow down towards each other. And there's going to be one point where each of the balls stops. And it's not necessarily going to be at the same point, right? One of the balls might stop before the other ball. So it's asking, how much would the spring be compressed when the 200-gram ball stops moving? So that's an interesting question because we need to think about it first from the point of view of energy. Where is the energy going? Before the collision, when the balls are just headed towards each other, and we look at the total energy of the system, we know that the energy is going to be 1/2 m1v squared, and this is the initial speed, right, of ball 1, plus 1/2 m2v2 initial squared. That's going to be the total energy of the system before they collide, right? That energy we know in an elastic collision, we're assuming this is an elastic collision, we know that the energy after is going to be the same amount, right, after the collision. So we know we would have like 1/2 m1v1 final and 1/2 blah, 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 right? But what happens during the collision? During the collision, the two balls are, they're headed towards the spring, and once the collision starts happening, once the spring starts to get compressed, what happens to that energy? Well, we all know when a spring gets compressed, it requires energy to do that. So some of the energy actually goes into the spring. So what it's going to look like during the collision is we're going to have 1/2 m1v1 final. We'll call it a final speed during the collision plus 1/2 m2v2f squared. But as I said, some of that energy goes into the spring, right? And we know the spring energy is 1/2 k delta x squared. A little bit hard to see that. I think you get the idea. So this is during the collision, right? So it's like there's still, during the collision, each of the masses is still going to have some speed. It's still moving a little bit, but it's also some of that energy is going into the spring. So the question's asking, how much would the spring be compressed when the 200-gram ball stops moving, right? So we know, in that case, this is going to be 0, the 200-gram, yeah, that's the ball 2. This is going to be 0, right? Our final speed of our ball 2 is going to be 0. So we can try to solve for x. But also realize we also don't know what our energy is going to be of our ball 1, because we don't know the speed it's traveling when this second ball has a speed of 0. This one won't necessarily be going at 0 speed. So we actually have to do a little bit more work here before we can plug it into this equation. And the thing we can do is we can use just our conservation of momentum, because momentum is always conserved, to determine the speed that this ball is traveling at when this one stops. Okay? With our conservation of momentum, we don't really care about the spring at all. Right? M2V2I equals M1, 1V1F plus M2V2F, right? We don't really care about the spring when we talk about conservation of momentum, because the momentum doesn't go into the spring, right? We assume that springs basically have 0 mass to make our calculations easier and stuff like that. So we're basically assuming there's no momentum that goes into the spring. So we need to determine during this collision how fast the mass 2 is going, right? Or mass 1 in this case, I guess, right? So if we plug everything we know about this situation into here, we can calculate the speed that ball 1 is going when this one stops, right? During that collision. So we can do that, and we can actually just solve for, if we rearrange this equation, we're trying to solve for V1F, right? We're trying to solve for this term right here. So if I just rearrange the equation, V1F is equal to, well, it's equal to M1V1I plus M2V2I minus M2V2F all over M1. Oops, not MI, M1. So if we just plug everything we know in here, we can solve for the speed of that ball 1, right, during that collision. So V1F, we need to plug in all our correct signs too. Be very careful. Remember, these are vectors. So our mass 1, again, we don't need to worry about the units because all the units for the masses are going to cancel out. So 250 times V1I, which is 3 meters per second to the right, plus 200 times -4 minus the second mass, which is the second mass, which is 200 times V2F, so the final speed, which is 0, right? So this term actually goes away, which is nice, all over mass 1, which is 250. See the grams and the grams and the grams? These 2 grams are going to cancel out with this unit gram, so we don't need to, we can plug in any unit there. We don't need to change it to kilograms. So when we do this calculation, we actually get that the final speed of ball 1 during this collision, when mass 1 stops, or mass 2 stops, is -0.2 meters per second. So during this collision, I'm actually just going to sort of draw this over here at this situation. So the spring at this time, the spring is being compressed, right? If this is M1 and M2. And M2 has stopped, right? So V equals 0. At that time, mass 1 is moving at the speed in the left direction of 0.2 meters per second. So that's what's happening at that point where mass 2 stops moving. So now, if we look at this, if we look at our energies before and after, we know they're going to be equal to each other because energy has to be conserved. We also know all our initial stuff, right? We know our initial masses, our initial speeds, and we also know our final masses and our final speeds. So the only unknown in setting this equal to this is going to be our delta x, right? So we can basically just plug everything in and solve. And it looks complicated, but it's not actually that bad. So I'm going to put this into here. I'm going to start a new line here. I'm going to call this conservation of kinetic energy, or conservation of energy, not just kinetic energy. Right? So we know it's going to be 1/2 M1 V1 I plus squared plus 1/2 m2v2I squared equals that energy while the spring's being compressed. So it's our m1v1f squared plus 1/2 m2v2f squared, right? But we also know our second mass stops. So that term is going to be 0. We'll come back to that in a second, because we still have to add our spring energy, right? Because some of that energy was turned into spring energy, K delta x squared. So a few things we can simplify here now. So we know that this is going to be 0 because our final speed of mass 2 is 0. Okay, that whole term goes to 0. We also know if we divide everything by a half or multiply everything by 2, these 1/2s will all go away. And it makes our calculation a lot easier. Then we can start plugging stuff in. One thing we should be careful with, though, remember our K that we're given in the question, which is 25 newtons per meter. Do you remember how 1 newton is 1 kilogram meter per second squared? So a newton is actually defined by the kilogram. So the problem is we can't use our mass as grams in this equation anymore because our spring constant is in newtons. And whenever you're dealing with newtons, you should always, have your mass in kilograms. So we should just convert back to kilograms for each one of these masses while using this equation. So just be careful about that. So mass 1 would be 0.25 kilograms times our initial speed, which is 3 meters per second, which is fine, plus m2, squared, I forgot to square it, 0.2 times 4 squared, and that should actually be a negative 4 squared, right? But is it going to matter when you square the energy or the speed? It's not really going to matter, right? Because when you square a negative number, it turns positive. Energy doesn't care about the direction, right? It just cares about how fast you're moving. And then we have 0.25 times the v1f, which we calculated as negative 0.2 squared. And that all is just plus the k, which is 25 delta x squared, right? So we can just solve for x in this equation. You can pause the video here, solve for x yourself, see if you get the same answer as me. So I get delta x is equal to 0.4665 or I'm just going to round to 2 significant digits, 47 meters. So still quite a substantial distance, and that's because the balls were moving fairly fast. And the spring was a very weak spring at 25 newtons per meter. So it makes sense that it's a big number. So at that point, the spring has compressed 0.47 meters. Because some of that energy from the balls, the kinetic energy, got turned into spring energy. Now realize when they finish bouncing off each other, all of that energy, that spring energy, is going to dissipate and turn back into kinetic energy, right? It's basically the spring is going to push back out, and it's going to end up back as kinetic energy of the balls. So let's look at the last question here. What is the maximum compression of the spring? So as these two things collide, there's going to be some point where the spring is the most compressed it can be. And you might be thinking, when does that happen? Did it happen when one of them, the objects was moving, was still, basically, was stationary, like in this case? Was it at this point? Or is it going to be at another point? What about if it's when m1 equals 0, right? The speed of m1 is 0. We don't know. It turns out the time that the spring is going to be most compressed happens when our final speeds are equal to each other of our two objects. When v1f is equal to v2f, so both of those balls are essentially moving together for an instant in time. And that's sort of like when the balls when the spring has sort of completely compressed, and then they start to move away from each other again. So it's basically for that split second where they're moving at the same speed, that is when the spring is going to be most compressed. Okay? This is when that happens. So we can actually do the same calculations as before, but now it's going to be a little bit simpler because we know v1f and v2f are going to be equal to each other. So in fact, what we can do is we can call them just vf, right? The final speed of both of these balls, right? So we can do that, and if you realize, this actually is a very similar calculation to one that we've done a bunch of times already with different types of collisions. Remember, the whole definition of a perfectly inelastic collision is when the final speed of the two objects are the same. So we're actually going to look at it as if, for a split moment in time, as if it was a perfectly inelastic collision. At least the calculation is the same. So we're going to do the same thing. We're going to need to use the conservation of energy, but before we do that, we need to know what that final speed is that they're traveling at. So to know the final speed, the easier way to do that is to look at the momentum, the conservation of momentum, right? So m1 v1I plus m2 v2I is going to equal our final velocities. But remember, when the final velocities are the same, we can sort of simplify the equation to look something like this. Remember that? So that's sort of our equation for when the two objects stick together at the end, or when they're traveling at the same speed at the end. So we can actually use that to determine the final speed, VF, right? We know VF is just going to equal m1 v1I plus m2 v2I all over m1 plus m2, right? And these are all vectors. So if we plug in the things that we know, again, remember taking into account the sign, and this is a case where we're okay to leave it as grams because the grams in the numerator and the grams in the denominator are going to cancel out, times 3 plus 200 grams times 4 meters per second. Oh, it should be negative 4 meters per second, right? Because it's to the left, all over 200 plus 250, right? So we can calculate that. And that's going to be negative 0.11111. I'm going to take a few extra decimal places here because it's not our final answer. So our final speed is going to be negative 0.01111. And that's when they're both going to be moving at the same speed. It's a little bit slower than this. So this wasn't the time that that was happening. It was a little bit, before or after that. So now what we can do is we can use our conservation of energy, right, with this final speed for both objects in order to calculate our maximum x. And we should expect it to be more than that, right? Because this one was when, not at that maximum point. So our answer should come out to a number that's bigger than that, more of a compression. So I'm going to leave that up to you. I want you to pause the video right now. I want you to try to figure it out yourself. Do the calculation yourself. Unpause it, and I will show you what the answer is. Strangely enough, our answer comes out to 0.47 meters again, rounded to two significant digits. And it looks like it's the same answer. It's not the same answer. This answer here, to more decimal places, would have actually come out greater than the answer here. This one came out less. We had to round this one more than we had to round this one. So this one is actually very close to that maximum compression. But to two significant digits, it looks like the same answer. This one was 0.46666, etc. This one was probably 0.474 or something like that. It was less than, or 0.464, something like that. Less than this one, even though they're very similar. So that is the maximum compression, okay? So just to recap, every elastic collision, this is happening, even if there's not a spring between them. The objects themselves will compress a tiny bit as they bounce off each other. They can't bounce off each other instantaneously. So some of that energy from the original kinetic energy of the two objects will temporarily be stored as elastic energy or spring energy within the objects or within a spring or something like that. And then when they rebound, basically that energy goes back into the two objects to move away from each other. So this always happens, even if you can't see it or even if it looks too fast to happen, it does always happen with any object.